Condensed electron configurations use the configuration of noble gases to simplify the process. So before we talk about how we do that, let's take a look at the periodic table and its relationship with electron configurations. This graphic here shows some electron configuration. So for example, hydrogen has one electron. Its electron configuration is 1s1. Helium 1s2. And then lithium has 1s2, 2s1, beryllium 1s2, 2s2. So there are a few things I want to point out on this periodic table. First, the periods 1, 2, 3, 4, 5, 6, 7 correspond to the highest energy level of the S and the P subshell. So if we look at hydrogen in the first row, the S subshell is being filled in n equals 1. If we look at the second period, the S and the P subshells are being filled for n equals 2. For the third period, we're looking at the S and the P subshells being filled for n equals 3. Fourth period, n equals 4. Fifth period, n equals 5. Sixth period, n equals 6. And seventh period, n equals 7. So that's very important. Another thing I want to point out is that in the first two columns, we have the S orbital being filled, or the S subshell being filled. And there are 2 electrons that can fit in the S subshell and 2 columns here. We call these first 2 columns the S block, and that's why hydrogen is in this block even though it's not a metal. Alright, now let's take a look at rows 13 to 18, and we see that the P subshell is being filled here. If we look at the second period, 2p1, 2p2, 2p3, 2p4, 2p5, 2p6, third period, 3p1, 3p2, etc. And then it's harder to see here, but the 4p, the 5p, and the 6p are being filled. The writing is smaller because there's a D subshell in there as well. So this block here is filling up the P subshell of whatever n level the period is, and because 6 electrons can fit in the P subshell, there are 6 columns. So this part of the periodic table is what we call the P block. Now helium is not part of the P block, but it is put in the noble gas family because it is a gas and its characteristics are very much like those of the noble gases, meaning unreactive. Now if we look at this block here where we typically consider the transition metals to be, this is where the D subshells are getting filled. Now I want to point out that the energy level of the D subshell is 1 less that of the period it's in. So we look at the fourth period, we're filling the 3D subshell. Fifth period, 4D subshell. Sixth period, 5D subshell. And since the D subshell can accommodate 10 electrons, in the D block there are 10 columns. So this block that we typically call the transition metals is known as the D block. Now down here where we see the actinides and the lanthanides, this is where the F block is being filled. And since the F subshell can accommodate 14 electrons, there are 14 columns here. And the F subshell has 2 energy levels below that of the period that it's in. So if we look at the lanthanides, they're in the 6th period, so the 4F subshell is being filled. And the actinides are in the 7th period, the 5F subshell is being filled. So we can look at the periodic table as being made of subshell blocks. And the periodic table, the way that the periodic table is set up, can be explained by the quantum mechanical description of electrons, mainly the subshells. And so it was very exciting to chemists to realize the relationship between the configuration of the periodic table and quantum mechanics. Now, going back to that periodic table that has the electron configurations on it, I want to point out one thing. When we get to the noble gases, which are the last column of each period, we notice that the subshells are completely filled. So the S and P subshells are completely filled, and once we get to the fourth period, we have D subshells. Those are completely filled, and once we get to the sixth and seventh period, we have F subshells, and those are completely filled. So the noble gases have completely filled subshells. So here are the electron configurations of 3 of the noble gases, and we can clearly see that all of the subshells are completely filled. So we're going to use that to help us write what are known as condensed electron configurations. So let's take, for example, phosphorus. If we look at the periodic table, here's phosphorus. It doesn't show on this one, but it has 15 electrons. So as we use the Aufbau principle to fill in each subshell, we notice that the first 10 electrons have the exact same electron configuration as neon. So what we can do is we place the symbol of neon in brackets, and that stands for the electron configuration of neon, and then we just continue with the rest of phosphorus's electron configuration of 3s2, 3p9, 3p6. So anytime you want to write a condensed electron configuration, we use the noble gas from the previous period, so the period right above the period that the element that you're looking at is in. And then you'll start the electron configuration at NS, 2s, 3s, 4s, 5s, 6s, where N is the period that the element you're writing the electron configuration is in. And then we move from left to right across the period from NS to N-1d if necessary, and NP. So let's look at an example to show how this would work. Let's write the condensed electron configuration for chlorine and for selenium. Alright, so here is chlorine right here, number 17. To write the condensed electron configuration, I look at the period above where chlorine is, so the second period, and I choose the noble gas at the end of that period. So neon is going to take up the first 10 electrons for the electron configuration of chlorine. Now, where do I start? Well, I start at the next period, the period in which chlorine is in. And I'm always going to start with the S subshell of whatever energy level the period that the element we're looking at is in. So since chlorine is in the third period, we're going to start with 3s2. And then we work our way across, and now we're at 3p. 3p1, 3p2, 3p3, 3p4, 3p5. So the electron configuration for chlorine has neon in brackets and then 3s2, 3p5. Now let's look at selenium. In selenium, we'll have to look at the D block. Here's selenium, number 34, and selenium is in the fourth period. So we use the noble gas in the third period, argon. So after argon, I go to the period in which selenium is in, 4s, so I start with 4s, and now as I go from left to right, I'm in the D block. And I want to remember that the D energy level is always one less than the period that these elements are in. So this is the fourth period. This is going to be 3d1, 3d2, 3d3, 3d4, 3d5, 3d6, 3d7, 3d8, 3d9, 3d10, and then 4p1, 4p2, 4p3, 4p4. So selenium with my 34 electrons, I use argon in brackets, and then 4s2, 3d10, 4p4.